All right, hello everybody, welcome back to another video. And in this video, I'm going to be doing something slightly different. Actually, you know what? No, scratch that. It's the same thing that I always do. But in this video, I'm going to be putting an emphasis on Lewis structures, meaning I'm going to be taking a look at the concept with the help of this question. So this question is from the November 2018 batch, it's from the paper 2. And I've seen questions like this come up a lot, very frequently in the exams. And you need to be able to draw Lewis structures, not only for such questions, but for a lot of other questions. And it is a very basic concept that you need to understand in order to score good marks. And I did not understand it for a very long time. And that's why I did not score well. But once you get it, you will be able to ace any topic in the chemistry syllabus of the IB, and even in the future, if that's what you decide to pursue. So let's take a look at it. The equations below in the equations show steps in the formation and decomposition of ozone in the stratosphere, some of which absorb ultraviolet light. Okay, and then they have given us these steps. Now, for the sake of this part of the question, 1A, we don't really need to look at the steps. They have just asked us, draw the Lewis structures of oxygen, O2, and ozone. So how do you draw Lewis structures? First step, look at what they're asking you to draw. Of course, first they've asked you to draw O2. This means that there are two oxygen molecules. Now, why do molecules come together? Why can't it just be O? Or why can't it just be Cl? Why does it have to be Cl2? You know, why do compounds form? Well, that's because they form bonds with each other, covalent bonds. And these covalent bonds help the atoms gain stability. And that's the main goal of bonding, it's to gain stability. Now in ionic bonding, we see that one atom gains electrons and the other one loses electrons, right? One atom has a gain, other has a loss, and that's what grants them stability. But when it's not ionic bonding, when it's covalent bonding is the sharing of electrons. And that is what is happening over here in O2. It's covalent bonding. And covalent bonding occurs between non-metals. And oxygen is not a metal. So between two oxygen molecules, covalent bonding would occur. And in covalent bonding, neither of them lose electrons. There is no loss of electrons. No loss of electrons. There is only gain. In a sense, you could think that there is only the gain of electrons. And how is it the gain? It's gain, they gain electrons through sharing them. So these two oxygen atoms, they decide to come together. Now, each of these oxygen atoms, so I'm just going to represent the electrons on oxygen number 1 using X's, and I'm going to represent the electrons on oxygen number 2 using dots. So now these two oxygens, they're roaming around, but they're unstable, they're not happy. Why are they unstable? Because they don't have a full valence shell, right? They should have 8 electrons. If they have 8 electrons in their outermost shell or their valence shell, they would be stable. But they don't have 8 electrons in their outermost or valence shell. They only have 6. Therefore, they're unhappy, they're not stable. So they need to become stable. And in order to become stable, they need to gain more electrons, right? They can't, if they lose electrons, that would kind of be working against what they want. They want to gain electrons so that they can become stable. If they lose it, it probably become, that would not be what they're looking for. They're not like alkali metals, which lose an electron to gain stability. These guys want to gain electrons, right? Both these oxygens are looking to gain some electrons. So they come to each other and both of them want to gain, right? This one wants to gain, this one wants to gain. None of them are willing to lose. So they say, all right, how about we share our electrons? Oxygen number 2 says, I have 1 electron. I'll give you this electron. I'll share this electron with you, and you share one of your electrons with me in return. So oxygen 1 says, okay, cool. And these guys, they start sharing this electron in this area over here. This is the sharing zone between them. And this sharing zone is called a bond. This is a bond between them. And a bond is always made up of 2 electrons. So a bond is always made up of 2 electrons. But this still doesn't satisfy them, right? Now, if we count how many electrons oxygen number 1 has, it has 1, 2, 3, 4, 5, 6, and this extra electron that it has gained from the sharing, 7. And if we count how many electrons oxygen number 2 has, it has 1, 2, 3, 4, 5, 6, and this extra electron it has gained from the sharing, 7 electrons. That's not stable. It needs 8. So oxygen number 2 says to oxygen number 1, hey, you know what? We're still not stable. How about we create another deal? Let's share. I'll give you 1 electron. You give me one of, or you share one of your electrons with me. So like, okay, cool. So they start sharing. Now you have a double bond. You have 2 deals going on, 2 bonds between them. And this bond is also made up of 2 electrons. So each of these bonds are made up of 2 electrons. Now, you must be thinking, okay, but technically, if they're sharing this electron, doesn't that mean that they've lost something? No, that's not true. Sharing an electron still means that the electron belongs to whichever atom is sharing the electron. It just means that the ownership of that electron or that pair of electrons has become common between the 2 participating atoms. So what I mean to say is that this electron still belongs to this oxygen, but now because of the bond, it also belongs to this oxygen, and vice versa. This electron still belongs to this oxygen, and now it also belongs to that oxygen because of the bonding. And it's the exact same case for this and any other electrons which are involved in bonding for any compound, right? They still belong to their original owner and may or may not belong to their, they still belong to their original owner or the original donor, and they also belong to the other compound that the electron is being donated to. That's why if you count the number of electrons on oxygen number 1 and oxygen number 2 after they have performed bonding, you will see that they are now stable because they have managed to gain a full outer shell, or they have managed to fill up their valence shell. So let's just count that. 1, 2, 3, 4, 5, 6, and let's not forget these 2, 7, 8. There we go. 8 electrons for oxygen number 1. Perfect. And it's the exact same case for oxygen number 2. They both are stable, and they have achieved this via covalent bonding or sharing of electrons. And what I have drawn over here, this figure that I have drawn, is basically the Lewis structure. Lewis structure shows the electrons and it shows the bonds. And this would be the Lewis structure of O2. Now, I hope that you've understood what I've done over here. And hopefully, in the future, if you ever encounter a question regarding Lewis structures, you will know what the answer to that is. Now let's look at the next structure, O3. Let's look at it, O3. So we have 3 oxygen molecules, right? This time, last time it was 2. This time it is 3. So let's just draw the electrons. Now, what I like to do is I like to put the electrons, I like to put the X's. I like to represent the electrons using X's on the central atom of any compound. And on the outer ones, I like to put dots. That's just how I like to do it. You could also do it the other way. You could put dots on the central one and crosses on the outer ones. It really doesn't matter. It's just all up to personal preference. It's a bit funky looking dots, but they represent electrons. So I'm just going to name each of these oxygens. This is oxygen number 1, oxygen number 2, and oxygen number 3. Okay. So oxygen number 2 is the central one, and he or she is approached by 2 other oxygen atoms. Now, oxygen atom number 1 says to oxygen atom number 2, hey, let's bond. I want to gain a full outer shell. I want to become stable. You can also become stable in the process. Oxygen number 2 says, cool, sounds like a good deal. Boom, they start sharing these electrons. Like I showed you in the previous example, this is how O2 would look. Now, if you look at this, bonding bit that has occurred between these two, you will see that both oxygen number 1 and oxygen number 2 are already stable. They have gained a full outer shell. They have become stable because this, what they have formed essentially over here is just the O2 molecule, right? So they've become stable. They don't need this extra guy coming in. They don't need the third oxygen. He's just kind of there. He's an extra, right? You don't need him there. So how is O3 formed then? If this structure already exists and it's stable, how does that extra oxygen get added and to form O3? Well, this is where we come in with a new concept. This concept is called a coordinate bond. Now, I've told you about, now think of bonds like deals, right? This bond, this deal that has formed between oxygen number 1 and oxygen number 2 is an equilateral deal, right? They both agree, I will donate 1 electron and you donate the other electron to the bond, right? They've agreed upon that. This oxygen says, I will donate 1 electron, you donate the other electron. They both agree. Same case for this bond. Now, this new type of deal, which is called a coordinate bond, this deal is a slightly selfish deal. In this case, the third oxygen, he approaches the second oxygen and says, well, you give me, you form a deal with me, you give me both your electrons. Well, what? What does that mean? What that basically means is that this oxygen, oxygen number 2, is going to form a bond with oxygen number 3. But the electrons in this bond, wherever the electrons that come in this bond, both of these electrons, remember how I told you earlier that a bond is made up of 2 electrons. In this bond, it's called a coordinate bond. In this bond, both these electrons come from oxygen number 2. So oxygen number 2 provides both the electrons in the bond. And remember, like I said, when a atom puts an electron into a bond, it does not lose it. It is simply sharing it with the other atom as well. So they both can gain stability. So in this case, these 2 electrons now belong to that guy, to oxygen number 3, and they still belong to the central oxygen atom as well. But in this bond, oxygen number 3 is contributing nothing. It gives no electrons to the bond. The electrons in this bond are all donated by oxygen number 2. So that is the deal. And that's why this is called a coordinate bond. And a coordinate bond is represented like this. It is represented with an arrow. And the arrow is going towards the atom, which is the selfish atom. It is the atom that doesn't donate anything. So that's how a coordinate bond, or a coordinate bond, a coordinate bond is represented in a Lewis structure. So this is the Lewis structure for O3. Hopefully you've understood what I've tried to do over here and what a coordinate bond is. I'll draw the O2 structure over here real quick as well. Now, one quick thing to touch upon before we go. You may be asking, why didn't this oxygen, oxygen number 3, why didn't it just donate? Why didn't it just also contribute another electron? So why didn't a normal double bond be formed like this? Why didn't that happen like it happened with oxygen number 1? Well, because if this would happen, oxygen number 3 will be fine. It will gain a full electron, it will gain a full outer shell. But oxygen number 2 will have an excess of electrons. It will have too many electrons. The number of electrons will exceed 8. Like if you look, let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because it's sharing more electrons. So oxygen number 2 will actually have 10 electrons. And that breaks our octet rule. The octet rule states that an atom can only have 8 electrons in its valence shell. And this breaks the octet rule because if we draw the double bond between both oxygens, it will mean that the central oxygen will actually have 10 electrons, and that exceeds the octet rule. However, there is an exception to this rule. Atoms in a compound can expand their octets, but this can only be done for elements which are in period 3 of the periodic table or later. And if you see where oxygen is in period 2. That means that it cannot expand its octet and it can only hold a maximum of 8 electrons in its valence shell. So that is the octet rule. Now, where do you see this octet rule taking place? Right? Do I have any examples? Yeah, sure I do. And let me show you an exception to the octet rule, or what do I mean when I say octet rule. So let's see. SF6. This is a compound, right? You have sulfur in the middle and you have 6 fluorines around it. Now, first things first, how do I decide which atom to put in the center and which atom to put on the sides? How do I decide this? Well, the rule is the most electron or the least electronegative element in the compound goes in the center. And in this case, sulfur is the least electronegative, and thus it goes into the center. And fluorine, you may know this, is highly, highly electronegative. In fact, it is the most electronegative element in the periodic table. So it goes outside, or it goes on the sides. And sulfur is the central atom because it is the least electronegative. Now, sulfur has 6 valence electrons. So I'm just going to draw that. So these are sulfur's 6 valence electrons. And fluorine has 7 valence electrons. Sorry. So yeah, these are your fluorines, right? Now each fluorine needs 1 more electron to gain stability. So fluorine number 1 will come to sulfur and say, hey, let's form a bond. All right, sulfur forms a bond. So now fluorine has 8 electrons because 1, 2, 3, 4, 5, 6, 7, and this electron it has gained from the sharing. And sulfur now has 7 electrons because 1, 2, 3, 4, 5, 6, and 7. This electron that fluorine contributed. So sulfur now has 7 electrons. So it needs 1 more bond. So sulfur says, hey, fluorine, to fluorine number 2. Hey, fluorine, you want another electron? Even I need another electron. Let's share. Fluorine says, cool. Here they go. They form a bond. And now you see, sulfur has a full octet or a complete octet. Fluorine number 1 and fluorine number 2 both also have complete octets. But the other 4 fluorines say, hey, I want a piece of the cake as well. I too want to gain stability. So sulfur is a very generous guy. He says, all right, I'll help you gain stability. And they all form bonds with sulfur. Now, you may be like, wait, what? These are not coordinate bonds because there is no arrows. How is it possible that sulfur can take 4 extra electrons? That would mean that it has expanded its octet. It has broken the octet rule. And yes, that is true. Sulfur can expand its octet because if you look at the position of sulfur on the periodic table, it is in period 3. And like I mentioned before, elements in period 3 or later can expand their octet. But notice one more thing. None of the fluorines, not a single fluorine has expanded its octet. All of them still follow the octet rule. And that makes sense because fluorine is in period number 2 and it cannot expand its octet. So hopefully you have understood the concept of Lewis structures with the few examples I gave you. That is the basics of Lewis structure. And if you know that the information, you will be able to crack any question. And I hope that I have done a good job at explaining that to you. Now, one final thing before we go. How do you draw a Lewis structure for an ionic compound? A compound with a charge on it. How do you draw that? For suppose something like OH minus. What do you do about this? What is this minus sign? Where does it go? So let's just let's draw our two elements, right? How many electrons does hydrogen have? Only one. How many electrons does oxygen have? Well, it has 6. Now this minus sign indicates that there is an extra electron. There is one extra electron just around this compound, right? You have one extra electron. So where do you add this one extra electron? You add it on the most electronegative atom. The most electronegative atom gets this extra electron that is there because of this minus sign. So this extra electron goes on oxygen because oxygen is very electronegative. And from there we go. These guys form a bond. Hydrogen only needs 2 electrons to be happy. It only needs 2 electrons to complete its outer shell. Oxygen has 1, 2, 3, 4, 5, 6, 7, and this one extra electron from the negative sign, it has 8. And therefore, this is the Lewis structure for OH minus. Now, supposing, just imagine this was 2 minus. If it was 2 minus, oxygen would gain 2 electrons because it's 2 extra electrons. Now, this is not possible, but I was just giving you an example. Now, what if it's something like NH4 plus? What if you're told to draw this compound? What does a plus sign mean? What do you do about that? In negative sign, you know that you add an electron. What do you do if there's a plus sign? Well, you guessed it. If there's a plus sign, you take off the electron. And if you have some compound like this, which is NH4, where it's H, 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 which atom do you take the electron off from? Well, you take it off the central atom. The central atom gets its one electron taken away from it. So nitrogen would actually have 5 valence electrons. You can check that in the periodic table. But because of this plus sign, we are going to take 1 electron away from it. That is how we form or draw the Lewis structure for elements with a positive charge. You take off 1 electron from the central atom. And there we go. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So it is complete. And each of the hydrogens have 2 electrons. That means all of their valence shells are also complete. So that is it for this video. I hope that you have understood the concept of drawing Lewis structures. And in future, if you ever encounter such a question, you'll be able to do it with ease. Thank you so much for watching. And I will see you in another video with a brand new question. And if you have any questions regarding this or any other concepts, please feel free to message me on my social media, send me an email or put it down in the comments below, and I'll be more than happy to help you. Thank you so much for watching.